This is the brief on static electromagnetic fields. All right, so today we're going to jump into a really cool physics puzzle. It's all about how we can use math to calculate these invisible fields and then, actually visualize where all their energy is hiding. So here are the two big things you need to know. Okay, first up, there's the math challenge. The source looks at how to compute this really tricky volume integral where electric and magnetic fields are interacting. So just imagine the electric field is kind of like pressure, always pushing from high to low. And the magnetic field? It's what we call divergence-free, which really just means it forms these endless loops with no real start or end. Now, here's the key. The volume we're looking at is wrapped in an equipotential surface, meaning the pressure is the same everywhere on the boundary. It's totally flat. And because of that, we can use something called the divergence theorem. It basically lets us trade a super messy 3D calculation for a much, much simpler one just on the surface. It's a genius shortcut. Okay, so that's the math. But where does the energy actually live? This brings us to our second point, energy distribution. We look at two totally different systems. With a single point charge, the energy density just plummets. It follows an inverse fourth power law. Think of it like a super sharp, intense spike of energy right at the source that pretty much vanishes as soon as you move away. But then you've got a solenoid, a coil of wire. Inside, it's completely different. The energy creates this nice, uniform bath, trapped and spread out evenly through the whole space. So the bottom line is this. Whether you're simplifying integrals or mapping out energy, the field's behavior depends entirely on the geometry of the system. Next time you look at a magnet, just remember all that invisible math that's holding its energy in place.